Hi, I'm Yusuo and I'm about to present to you about my project, the focal shape manipulation by annular appetizer. I should participate the conference on Friday, so I can't make speech in that day. Instead, I made a presentation video with the instructor's permission. So, off I go. First, the basic theory. I don't think the maths are necessary for understanding the concept of Fourier optics. Of course, it is required to solve the equation to predict the shape of beam at a certain position, but for understanding, I don't think it is necessary. The Fourier optics is about aperture. It is about treating all the features in an object as aperture with different shape and size, and it is about how these aperture information can't be transferred to other places through imaging system. Let's assume that someone is looking at the skyscraper. If he or she looks at the object far away, then the image generated in the retina can be predicted with simple geometrical optics like this. It also can be predicted in closed object case like this. With geometrical optics, the image of closed building is just magnification from far building image. So if your retina has some infinite number of pixels and all details in buildings such as windows will be retrieved by simply magnifying the object. Magnifying the image, I mean. If we're living only with geometrical optics world. But it is not, because the light reflected from the object is diffracted based on Huygens law. So this building is some of various apertures. The largest aperture it has is square aperture. This, whole shape of building. It acts as some kind of reflective aperture and diffracts the light, but not that much, so information about this large square propagates with smaller angle, which makes the wave by this more like plane wave. But on the small apertures like a window, it is different. It diffracts the light more drastic than the whole building shape, and light containing the information of the windows more look like spherical wave. So if you look at the building far away, then the whole shape of building still will be recognizable, but all details are gone because it just passed by your eyes like this, because it has larger angles, so details has larger angles. So even if the retina has infinite number of pixels, the details in the object will be gone if you look at the object far away. It means the performance of imaging system is limited, and it is computable with Fourier optics, and that performance is resolution. So that was the concept, and my project problem is lands with annular appetizer. I assume that the appetizer mask is placed just before the lens like this, and it blocks the light at the flex circle A, and this blue area just transmits the light. No phase shift. So the field intensity map at certain actual position G under such condition is U, and can be calculated like this. The UL is transmittance map of appetizer, and K is wave number, F is focal length of lens. UXY, field map UXY at certain position Z can be described like this, and this term is Fourier transform of this UL prime multiplied by this exponential term, and I set focal length of lens as 5 mm, An instant beam shape has normal distribution circular beam with 1 mm WHM size. I set field size as 5 by 5 mm square fields, and calculation range was 0.1 mm around the focal plane, and I observed the change of focal shape as the R value increases. R value, this one. And this is MATLAB script. The first line is clear all for deleting all variables before the calculation initiates, and this one's about setting the wavelength, wave number, ratio R, and calculation range G, and focal length. And this is about field map U, and the mesh grid, which look like this. It is for ease of calculation, and XX and YY is normal probability distribution map at x-axis and y-axis. So instant beam shape is calculated on this line, which looks like this, and then I create this circle with mesh grid. Then on these two lines I created mask, and I adapted mask here, and this one is UL prime, and these for loop is for calculation of intensity map inside the calculation range, and these commented lines are for saving the result, and KKK is for monitoring progress. So this is result. This is intensity map inside the calculation plane, and at R equals 0 it shows beautiful Gaussian shape, and as R increases the wavefront scrambled and just look just like eddy pattern. What is it's more like eddy pattern. The interesting is the beam size at focal plane, say focal size looks similar in all the three cases. Look at this at focal plane, and alright, I'll do it again. Looks similar though. Then I plotted the intensity axially and laterally. First, axial position and intensity. The distribution gone wider when the R is increased. That means with the same lens, the focal depth can be longer when the beam is apodized. Then I also observed the focal size actually. Actually the WHM is decreased as the R increases. There is fluctuation in apodized cases, but I think the lateral resolution of lens can be enhanced with beam apodization. So here's summary. The shape and length of focused beam by lens can be adjusted by annular apodizer, and the apodizer increases the focal depth while the focal size is decreased. So this is the end of my presentation, and thank you for listening.